more than welcome, or you can just kind of follow up here. Okay, chapter 15 really just kind of picks up where 14 left off. What we're really looking at in chapter 15, if you look at the title, it says forces acting in different directions. The first two sections really kind of lay the foundation for how we're going to do this. So far, we've really just looked at forces acting in a line, like in a straight line on an object. And in the real world, it doesn't really work that way. So we're going to be building up to how we can look at forces acting in different directions on an object to figure out what we call it what the net force is, what the total force is. So 15.1 is very straightforward. So let's go through it. It says in chapter 14 you learned that if we exert a force on an object and it does not move, there must be some other force acting on the object in equal strength in the opposite direction. We say that the forces on the object are balanced. Okay, so when there's two forces, the example here is the metal washer. We have two spring scales pulling in opposite directions. For this object to stay at rest, it means the two forces acting on it are balanced. They balance each other, which means it's the exact same strength pulling in opposite directions. So same strength, opposite directions. It's kind of like tug of war. I use that example a lot in this chapter. If two teams are pulling with the exact same amount of force in opposite directions, nobody's going anywhere. Okay, so for two forces to be balanced, they must be the same strength in opposite directions, along the same line. What that means is just in a straight line. Okay, what we're going to build up to is forces acting not in a straight line, and then what do we do with that? Okay, so this part's pretty easy. When it's just in a straight line, if the forces are balanced, the object stays at rest. When they're acting in a line, you can basically use what they call signed numbers, right? You can say if one force is 8 newtons in this direction and the other force is 8 newtons in this direction, just assign one of them a negative value, and then when you add them up, they're going to equal 0. So when forces are balanced, the sum of their forces is 0. So we say the net force is basically just the combination of all forces acting on an object. Their net force would be 0. So really to accommodate that, when they're acting in a straight line, you can just assign one of them a negative value, and then when you add them, you get to 0. You can tell when any number of forces along a line, again, in a straight line, are balanced by expressing their directions and strengths.
Good afternoon, teachers and students.
Hang on a sec.
So great. All students on the list for perfect attendance, you are invited to come to the ice cream social in the cafeteria. All students on the list for perfect attendance, please report to the cafeteria.
Congratulations to you. Enjoy. Okay. Excellent, excellent. Okay, we're going to keep going. Okay, let's keep going, guys. Shh. Thank you. My turn. Okay. So it says you can tell whether any number of forces along a line are balanced by expressing their directions and strengths as signed numbers and adding in this way. If the sum is 0, then the forces are balanced. This is actually quite simple, but I'll tell you what, when my students took the chapter 14 test, I thought this was one of those gimme questions where I'm like, everyone's going to get this right because it's so easy. For some reason, they completely just struggled with it. I'm not really sure why. So let's talk about this. In this example, the object that's being pulled on, which is this metal washer, is at rest, which means all of the forces acting on it must be balanced. So their sum must be 0. The only difference is now we have two spring scales pulling in one direction instead of just one spring scale. So two scales pulling this way, one pulling this way. It doesn't matter that there's two separate forces acting on the object because they're moving in the same direction. So we're still talking about forces acting in a line. So if one spring scale is pulling with 4 newtons of force, the other one's pulling with 10 newtons of force, and then the one on this side is pulling with 14 newtons of force, all we have to do is either make both of these negative and then add them up, or make this one negative and add them up. So 10 and 4 going in one direction is 14, and then 14 going in the opposite direction. If one of those values is negative, when you add them, you get 0. Okay? So if you have more than one force pulling in the same direction, you just add those two together. It's kind of like, if you're trying to move your couch at home and you have two people on one end of the couch pulling in one direction, the combination of their force is what's acting in that direction. So if I'm pulling with 10 newtons of force and the person next to me is pulling with 10 newtons of force, our combined force is 20 newtons in that direction. So when forces are acting in the same direction, like these two spring scales, you just add them together, basically. Okay, and then you can balance that by looking at the force going in the opposite direction. Assign one of them a value of negative, and then you add them and their sum is 0, so the object is at rest, the forces are balanced, and it's not going anywhere. Yes?
How do you decide whether any number be a negative or positive?
Yes. As long as, if you're going to assign one of the forces on this side to be negative, that means they both have to be negative.
Oh, okay.
Yep. Okay, so just choose one direction to represent negative and the other one to represent positive. It doesn't matter. Either way you do it, you still come up with a sum of 0. So that's fine, either way. Okay? So forces acting in a line, we can figure out what the net force is by applying a negative sign to one side and then adding them and figuring out what the net force is. Now this also works if the object is moving. Let's say this is 10 and this is 4, but on this side it's 15. That means this force going in this direction is greater, so the object's going to move in that direction. So this doesn't just work when the object's at rest. It can work regardless of what the values of the forces are. You just assign one side a negative and then add them up. So, for example, let me see a piece of paper here. And this is like the test question. So when we hopefully get to the point where you guys can see that, the chapter 15 test, you'll see what I'm talking about. So if I have a metal washer here and I'm pulling in this direction with, let's say, 20 newtons of force, and there's a force going this way, that's 10, and a force going this way, that's 5. I can make both of those negative, so negative 15 plus 20, which means it's going to be 5 newtons of force going this direction. You guys see that? So this same thing works even if the object's not at rest. So you can figure out what the net force that's acting on the object by assigning negative values to one side and then adding them. This only works when they are acting in a line, in a straight line. So forces going to the left and forces going to the right, or forces going up and forces going down, exactly the opposite direction of each other. Okay? Only when they're acting in a line. So that's 15.1, pretty straightforward. I'm not going to read 15.2 to you. You guys can read that on your own. I'm just going to give you my version of it. So what they introduce in this section is the concept of a vector. A vector is basically any quantity that describes both the size of the force and the direction. So a vector quantity includes both size and direction. You may also see the word magnitude. And I don't know if that came up in the last chapter or not. Magnitude just means size. It's the same thing. So if you see the word magnitude or the word size, they mean the same thing. So a vector quantity shows size and direction. So now what they're introducing is how we can use vectors. So a vector basically is drawn as an arrow. So the length of the arrow will represent the size of the force, and then the direction of the arrow represents the direction of the force. So when we deal with vectors, we come up with the concept of a proportionality constant, which you guys have heard the word proportionality constant before. But to really understand what force is being represented by a vector, we need to know what the proportionality constant is. I always like 1 centimeter per newton because it's so easy. So every centimeter would represent 1 newton of force. So a 3 centimeter line would represent 3 newtons of force going to the, what direction is that, right? To the right. Okay. So a 6 centimeter line would then represent a 6 newtons of force going to the right. A 9 centimeter line would represent 9 newtons of force. Now the proportionality constant can be different. The thing that comes up with the test questions and the REE questions is what is the proportionality constant and making sure we apply it correctly. So another example would be we could do 2 centimeters per newton. So they give us the math behind it in the book. I prefer to think about this just logically. A 2 centimeter per Newton proportionality constant means every 1 Newton of force is represented by a line that's 2 centimeters in length. Excuse me. So a 2 centimeter line would represent 1 Newton of force in this case. So when you change the proportionality constant, the length of the line is going to change depending on what the force is. A 4 centimeter line would represent 2 newtons of force, and a 6 centimeter line would represent 3 newtons of force. That's when the proportionality constant is 2 centimeters per newton. So when you look at proportionality constants, just think about what it actually is what it's saying to you. In this case, every 1 newton of force is equal to 2 centimeters. Or in this case up here, every 1 newton of force is represented by 1 centimeter. Okay? Now here's where it gets tricky. Only because we tend to not pay attention sometimes to what the proportionality constant is saying, you can flip it around and do newtons per centimeter rather than centimeters per newton. So when you guys are working with proportionality constants and vectors, you must pay attention to what unit they're using for the proportionality constant. If you kind of talk yourself through it, you can logically make sense of it. In this case, every 2 newtons is represented by 1 centimeter. So I can measure my line, and if I have a 1 centimeter line, I go, okay, 1 centimeter is equal to 2 newtons. Okay, so that's a 2 newton force. A 2 centimeter line would represent 4 newtons of force, right? Because every 1 centimeter is 2 newtons, so 2 centimeters would be 4 newtons. And then same thing with 3 centimeters. You can basically see how that would work. So when you guys are looking at proportionality constants and measuring vectors, which you'll do quite a bit of in chapter 15, is measuring those lines in centimeters, the only trick is just paying attention to how the proportionality constant is written. If it's written as centimeters per newton or newtons per centimeter. Just talk yourself through it in terms of what it means. I think here, logic really comes more into play than the mathematics of it, because if I try to sit down, because it goes through the mathematics of it for you guys in the book, and you can read about that, I think that tends to be more confusing. I think if we try to just approach it logically in terms of what the unit represents, we'll be in a lot better shape that way. So that's section 15.2, is really just introducing the idea of what a vector is up here, and then introducing the proportionality constant and how the vectors would look depending on what the proportionality constant is. And remember, the big picture here is how can we represent a force in terms of using a vector. Okay, so the line itself represents the strength of the force. And of course, you know, the logic behind it is the longer the line, the greater the force. So that's one way for us to represent forces in terms of using vectors. So that's 15.2. That's the gist of that. And again, you guys can read through that. It spells out exactly what I just said. I think my version's probably a little bit easier to understand, though, hopefully. Did you guys have any questions on that? You good there? Okay, good. Oh, good. We have plenty of time then. I'm going to stop recording real quick.